Watch these two double pendulums begin almost identically. For a moment, their motion seems to match. Then one swings left, the other swings right, and their paths separate completely. If the laws are deterministic, how can prediction become so difficult? The tempting answer is that the universe has stopped following rules. But chaos does not mean lawlessness. In a chaotic system, the rules can be exact, the starting state can be specified, and the next state can still be determined in principle. A double pendulum is a simple demonstration. One pendulum hangs from another, so each arm affects the other through gravity, tension, and motion. The result is a coupled system. Changing one part changes the forces acting on the whole arrangement. Newton's laws still apply. The equations of motion are not random instructions. They connect the positions, velocities, masses, lengths, and gravitational acceleration at one instant to what happens next. The difficulty comes from the coupling and the nonlinearity. Now change the starting angle by a tiny amount, not a new law, not a random shove, just a small difference in the initial state. At first, the two motions remain close, but the separation grows until their later positions no longer line up. That distinction matters. Deterministic means the same complete state leads to the same future under the same equations. Chaotic means nearby starting states can separate rapidly. So the system may be predictable in principle, while our real prediction becomes fragile. To see more than the moving arms, physicists can track a system in phase space. Instead of drawing only where the pendulum is, we track coordinates together with velocities. A path through that abstract space becomes a fingerprint of the system's motion. Prediction has a horizon. When uncertainty in the starting state is small, a short forecast can be useful. As the trajectories spread, the uncertainty band widens. Beyond a practical horizon, a precise long-term path is no longer trustworthy, even though the equations remain unchanged. Chaos is not the same as randomness. Randomness describes outcomes that the model treats as unpredictable or not fixed by a known deterministic rule. Chaos describes deterministic rules whose outcomes become extremely sensitive to tiny differences in the starting state. The double pendulum is not just a clever toy. Chaotic behavior can appear in many deterministic models, including idealized weather dynamics and fluid motion. The lesson is not that every forecast is hopeless. It is that forecast quality depends on scale, uncertainty, and how sensitive the system is. Computers face the same problem. A simulation stores numbers with finite precision, while a real measurement is never perfectly exact. In a sensitive system, those tiny differences can grow. A different-looking simulation does not automatically mean the laws were violated. This is the careful meaning behind the butterfly effect. It does not mean one literal butterfly guarantees a particular storm. It means that in a sensitive system, a small change can influence later outcomes, making long chains of cause and effect difficult to forecast in detail. So classical mechanics is both powerful and humble. Its equations can be deterministic, exact in form, and still unable to give us unlimited practical prediction. The limit is not a failure of rules. It is a limit on the information we can know and preserve. The double pendulum teaches the final lesson of this series. Simple laws can create complicated motion. Understand the assumptions, track the variables, respect uncertainty, and ask not only whether a system has rules, but how far those rules let us predict. This is James Physics 101.